Before we conclude for the day, I just want to teach you about one other important boundary condition, and then we will have almost a complete set of boundary conditions. And this other type of boundary condition we can get at by thinking about a question, which is what happens when we have an infinite potential? What happens if V naught here goes to infinity? Now, if V naught goes to infinity, when we look at our solution here, you'll notice the behavior of my solution depends on two things, right? There's some overall factor that just sets the scale of the function. The other things it depends on, though, are the values of k1 and alpha 2. So we'd better consider how those behave. So k1, you will recall, was the square root of 2m over h bar squared times the difference between the energy and the potential. But in region 1, it's just the energy. And these quantities, as you will begin to learn, always have the positive values of things. So that's k1. Alpha 2 is again the square root of 2m over h bar squared times the difference between the potential and the energy. But again, we've defined our alphas and k's, so what's inside the square root is always positive, and the potential is more than my energy in this region, so I have this result. Now, to get to my question, as the potential V naught goes to infinity, nothing special happens to K1. There's nothing really changing there, but alpha 2, you will notice, actually also becomes infinite. Okay, well, with alpha 2 going to infinity, I think we can now figure out what our function would do. So phi of x now is going to approach, and of course we've got two different regions with two different characteristic behaviors. Now, as alpha 2 goes to infinity, you will notice this first term then is going to go to 0. And I will just be left with the b and the sine term. So when x is less than 0, I have only b1 times sine of k1x, and this is what I find when x is less than 0. For the alternative, when x is greater than or equal to 0, for that alternative, let's see, on this branch, I have, oh, look, again, I have k1 over alpha 2. Again, this term will, as alpha 2 goes to infinity, will go to 0 for two reasons. One, the prefactor is 0, and also it's a super fast exponential decay. So I would then have just 0 for x greater than or equal to 0. I can sketch what this kind of wave function would look like. And we learn in an interesting lesson here. So here's phi of x. Here's x. So in region 2, when x is greater than 0, here's the x equals 0 point, the wave function itself is 0, right? And that kind of makes a lot of intuitive sense, right? I mean, if the energy there is truly infinite, right, then even a quantum mechanical particle can't spend any of its time in that region. It just decays exponentially with a super fast exponential decay, so no matter what I hit this thing with coming in, it will very quickly decay right to 0. For x less than 0, I have this sine function, and the sine, remember, we imagine b1 is positive for the sake of argument. The sine function goes to 0 when x is 0, so that's nice, so my wave function will be continuous. And of course, when x is negative, the sine function is negative. So I'm looking at a sine wave that's going to 0 from negative values, and then it just has its normal sine wave type behavior. So this whole curve then, I'm just coloring it in a little bit, but this shows you exactly what I expect my wave function to do under such a condition. So there's an important lesson here. And this then takes us to our final boundary condition for the day, which almost, by the way, completes our set of boundary conditions. We have just two more boundary conditions that we will be learning about, but these are enough to solve most problems. The other ones have something to do with delta functions and something called scattering states, which we will get to later. So boundary condition number 3 we just learned is that if the potential V of x goes to infinity over a non-zero region, right? Over a non-vanishing region, I will call it. So I'm not talking about a delta function, right, where the potential goes to infinity just at a single point, but over an extended region. Maybe that's probably a better way just to put it more intuitively. Over an extended region, right? When that happens, right, because we have that super fast exponential decay in those regions, right, the wave function immediately, the boundary condition then has to become then psi of x, right, has to equal 0 throughout that region. That is throughout the region. And of course, because wave functions are continuous, that also means and at the boundaries of the region. Boundaries, right? Because we could have more than one boundary. Boundaries of the region. And we can see that playing out here, right? Psi of x is 0 inside my region, and it also has to hit 0 just at the edge of my region. So that's my third important boundary condition. Now, if you've been paying attention to the lecture, right, you'll notice something at first maybe a little disturbing here, and you'll notice that now I actually have a kink at this location, right? That means there is a discontinuity in the slope. The slope on this side is 0, and here the slope is some positive value. It's definitely not 0. The first derivative is not continuous. And you might think, wait a minute, we proved a theorem that the wave function the slope has to be continuous across a boundary, that there can be no kinks. But remember the condition on our theorem. The condition on our theorem was that this potential V had to stay and maintain a finite value for the theorem to hold. When the potential is infinite, we can have a kink. So I'll just make a little note down here. Note, for infinite potentials, for V that can, I guess I just infinite. For infinite V's, we can have a kink in the slope. But my point to you is that as long as V is finite, of course, you wouldn't expect such a kink. So that's just a little footnote there. Very good. So I think we've got a very good handle now on all of the key boundary conditions. And also we now have a workable, even in the case where the potential doesn't go into infinity, we've got a workable solution to our time-independent Schrodinger equation for our example of the potential step. What we will look at next time is, in fact, how we can pull all of the information out of this wave function in order to determine what happens quantum mechanically when a particle encounters a step.